Today, we're going to peel back the layers on this really cool tech that lets us see problems that are completely invisible to the naked eye, and even to a standard thermal camera. We're talking about lock-in thermography. So yeah, let's dive right in and look underneath the surface.
You know a regular thermal camera? It's awesome for seeing heat right on the surface. It gives you this beautiful two-dimensional heat map. But what if the problem, a crack or some delamination, maybe a short circuit, what if it's not on the surface at all? What if it's buried deep inside? I mean, how are you supposed to find a ghost in the machine?
And, that's really the big limitation of a simple thermal photo. All you get is this static, flat picture. To find something that's hidden, we can't just look at the temperature on the surface. We've got to go beyond that simple image. We need to add a whole new dimension, depth.
And this right here, this is the solution. And it's pretty brilliant. So instead of just, blasting an object with steady heat, which just gives you that flat 2D map we talked about, lock-in thermography does something way, way smarter. It pulses the heat source, on, off, in a perfect rhythm. This creates a dynamic, a moving heat wave that actually travels down into the material.
Okay, so this heat wave, this is our secret weapon. As it travels into the object, it's like a little probe checking out what's inside. And when it bumps into something, say a defect or a different kind of material, really anything unusual, it reflects, it bounces back up to the surface. And by analyzing that wave that comes back, well, that's how we can finally figure out what's happening underneath. All right, so the camera is sitting on the surface, and it's looking for two key clues from that returning heat wave. First up, we have amplitude. Just think of it like the volume or the loudness of an echo. It's the strength of that temperature change on the surface. A really strong signal means a whole lot of heat is bouncing back. It's a direct look at the thermal response right there.
But the second clue, now this one is arguably even more important. It's called phase. So if amplitude is how loud the echo is, phase is all about how long it took for that echo to get back to you. It's the delay between when we sent that pulse of heat in and when we actually see its effect come back to the surface. That time delay, it tells us pretty much exactly how far that heat wave had to travel.
So let's get to know our two little detectives here, amplitude and phase. Each one's giving us a totally different piece of the puzzle, and when we look at them together, we can start to build a really clear picture. But, as you're about to see, one of these is way more reliable for sniffing out those really well-hidden clues. Okay, so what's so cool here is when you put them side by side. Amplitude, right? It tells you how hot something's getting. That's useful for sure, but it gets fooled really easily, like a little fingerprint smudge, a reflection, even a different type of paint. All of that stuff can mess up the amplitude reading. But phase, it only cares about time, so it's incredibly robust. It couldn't care less about smudges on the surface. A longer delay just means one thing. The heat went deeper. Simple as that. So here's the bottom line. Amplitude is good for how hot, but phase is the absolute best for how deep. And honestly, this is the superpower of lock-in thermography. Because that phase image, it gives us this clean, super reliable map of where things are depth-wise, and it's totally immune to all that visual noise on the surface. It's almost like having X-ray vision, but for how long it takes heat to travel.
But wait, it actually gets even better. Because now that we know what to look for, we can actually control where we're looking. This isn't just some one-and-done picture. It's a completely tunable system. We can literally control how deep that heat wave goes. So how do we do that?
So let's say we want to find a really shallow flaw, something that's hiding just under the surface. What we do is we pulse the heat really, really fast. This high frequency means the heat wave just doesn't have time to go very deep. It pretty much stays right near the surface, and that gives us this amazing high-res map of what's going on just a tiny bit down.
Now, on the flip side, what if the problem is buried way deep inside? Well, then we just slow the pulse way down. Using a low frequency gives that heat wave plenty of time to really soak deep down into the material before it bounces back. And that's what lets us find those much, much deeper flaws.
And that is what makes this whole technique so incredibly powerful. By just changing the frequency, it's like we're focusing a thermal lens. A high frequency, that's our close-up, high-res view of the surface. A low frequency lets us kind of zoom in, deep inside the part. It's that tunability that just makes it such a flexible and powerful tool for inspections. Okay, so let's tie this all together.
What really makes this whole lock-in thing such a complete game changer when it comes to finding stuff we can't see?
Well, first off, it just cuts right through all the random thermal noise because it's only locking onto the signal at our exact frequency. Second, it unlocks real, honest-to-goodness depth information by using that phase delay we talked about. Third, it's totally tunable. We can change the frequency to focus shallow or deep. It also just naturally ignores any steady background heat. And to top it all off, you get two amazing images for the price of one. Amplitude tells you how hot, and phase tells you how deep.
So this technique basically transforms heat from just being a flat surface measurement into a full-on, three-dimensional probe. It lets us do things like inspect composite materials, hunt down failing circuits, and check for quality in ways that were honestly pretty much impossible before. Which kind of leaves you with one big question, right? Now that we can actually see heat in 3 dimensions, what other invisible worlds can we start to explore?